It's Thursday. It's time for the news. The mathematics news. Okay, this afternoon we are talking about power. Power is part of the same chapter on work, energy and power. It's the last section. And power is defined as being work done over time. So if something is more powerful, it can do more work in less time. So power is equal to work done divided by time. Work done is measured in joules, time is measured in seconds, and power is measured in watts. Okay, and the unit of watts is usually written as just a capital W. Work done, of course, is measured in joules, that's a capital J, and time in this case is measured in seconds. Okay, strangely enough, we have some fantastic other ways of writing the power formula, because we know that work done is equal to the force times the displacement. So if we have power is equal to force times displacement divided by time, at a particular moment, we can say that power is equal to the force multiplied by distance divided by time, which is speed or velocity if we're using vectors. So we have this version of the power formula and we have this version of the power formula, and both of them can be used in different contexts. They're great. Let's have a look at some examples. Oh, I should mention as well, I think that the force involved here doesn't have to be constant. One of the big things about the work, energy and power questions is that acceleration does not have to be constant, the force does not have to be constant. You can look out for these questions involving power because they don't tell you the constant acceleration. They tell you there is something involving energy, there is something involving kinetic potential, something involving power, and if you can see that in the question, you know what you have to do. Okay, let's have a look at some examples. So first of all, just to give you an idea of where power can be in a question, we've got a question here that's talking about Mr. Kennedy, oh, that's me. He's carrying a penguin up 11 meters worth of some steps. So he's going up 11 meters, increasing the potential energy. It takes 45 seconds. So we're dealing with something involving time here. We want to know how powerful or what sort of power was involved here. And so we can use this formula. We can work out the amount of work done. We know it took 45 seconds. It says here I start and finish at rest. So at the beginning of the whole journey, there is no potential or kinetic energy. At the end of the journey, there's going to be no kinetic because I'm not moving, but there will be some potential because I've gone up. Oh, that was my speaker running out of batteries. Okay, so at the start, no kinetic, no potential. Then we've got the work done by me, carrying the penguin, very hard work. There's no resistance involved in this question, and at the end we have no kinetic because I'm not moving. It says it starts and finishes at rest, but there's potential here, which is the mass of the penguin times mgh, so it's times 10, the acceleration due to gravity, and the height here was 11 meters. So the potential energy is 300 times 11, which is 3,300 joules. So the work done must be equal to 3,300 because it's all of this lot is equal to this. So the power involved here is the work done, which is what I did, 3,300 joules divided by the amount of time it took, and I get the power in the situation. Let me see, that comes out to be 73.3 watts. And that's the three significant figures. And if I'd done it faster, that means that I would have had less time, so I'd have got more power. If I'd done it slower, it would have been less power. If it had been more work involved, it would have been more power in the same amount of time. So there's this relationship between the amount of work you can do over time. Okay, my next example involves more of a sensible question. There's a car which is moving, and it's got a power of 30 kilowatts, that's 1,000 watts, and it has a top speed of 35 meters per second. What is the force exerted by the car's engine when it's traveling at top speed? And this is a lot of words, but it really is just asking what is the force, and the connection between the force and the power and the velocity is summed up by this formula. Power is equal to the force involved multiplied by the velocity. And we know this is a 30 kilowatt powered engine, so we have 30,000 watts. The force is what we're looking for. The velocity was 35, and so we can work out what the force the engine was pushing. 30,000 divided by 35 is apparently 857 newtons. That's not exact, it's rounded to 3 significant figures. Okay, and that's the amount of force that was coming out of the engine, which had this much power, if it was to reach this speed. Then the question goes on to ask, how much is the work done by the force over 90 seconds? So there's this version of the formula, but there's also the other one, which says that power is equal to work done over time. And here we don't know the work done, but we do know it happened over 90 seconds, and we know the power of the engine. So we can then work out that it's 30,000. It's equal to the work done divided by 90, and that makes the work done come out to be 27,000 kilojoules. So the work done is equal to 27 and then 0000 joules, which is the same as 2,700 kilojoules. Okay, so we have all these connections between power, velocity, forces, work done. It's all connected, and sometimes you get questions that involve power on top of what you already know, and you can piece together the situation. Okay. So in this question, it says Mr. Kennedy pushes a 50 kilogram penguin on roller skates. There's the penguin, there's me, pushing it that way. Why did he push the penguin? Well, that's easy. It's because I hate penguins. I can't stand them. The little penguins with their tiny beaks. Arrgh. Okay, so this is more of a larger, sensible question that involves a car which is going up a hill. It's an inclined hill, and we're going to have to take into account the fact that the weight can be split into perpendicular and parallel forces, and some of the force is going to be going down the slope this way, and we need to break that down and then use it in the question. But here we're not talking about just forces involved, we've got power as well. So it's a car with power 54 kilowatts. At a particular instant in time, it's going at 20 meters per second. We've been given a resistance to motion and the mass of the car, and we've been asked to find the acceleration. What we can do is we can use F equals ma eventually, but we need to work out what the driving force of the engine is. And we can do that by using the power formula with the power and the velocity at that particular instance. One of the key things about this question, though, is it talks about the resistance to motion. The resistance to motion does not include the weight of the car. There is also a weight force that's pulling it backwards. Unless the question said total resistance, then you could presume it includes the weight of the car. But here it's just the resistance to motion, it's the friction on the road, presumably. But we have to break this down, and I can do that just like we've always done. We've got 5 degrees here, so there's going to be 5 degrees here. That component there going horizontally is going to be 13,000 times the sine of 5, and the one going perpendicular to the slope is 13,000 cos of 5 degrees. So we've got this extra force here, which is 13000 sine of 5, and this one going down this way is 13,000 cosine 5 degrees. Okay, so let's put everything together. Before we do F equals ma, we're going to say that power is equal to the driving force in this case, multiplied by velocity at that particular instance, because we're just talking about the power of the car. This is the driving force exerted by the engine of the car, and it's going 20 meters per second. And once we've got that, we can work out everything else. So power was 54,000 watts. The velocity was 20, which means the driving force of the engine comes out to be 2,700 newtons. And then using everything we know here, we've got the driving force, take away the resistance to motion, which presumably is friction, take away the weight component, which is horizontal. We can say that 2,700, take away 800 for the resistance, take away 13,000 sine 5 is equal to the mass of the car, which was 1,300, times the acceleration. Tidy this up, divide by 1,300, and we get the acceleration back as 0.590 meters per second squared. That's been rounded to 3 significant figures. So just to recap, power is equal to the work done divided by time, but also it can be power is equal to the force involved at a particular instant times the velocity of the object. And both of these are equally useful. Does Mr. Kennedy use his power responsibly? Well, if you want to be responsible, you should be doing exercise 9A, 9B, and 9C. If you can manage to cope with these ones, then you're in a good position to master this whole topic, which is fantastic.